Hey guys, welcome to Blockchain Fundamentals, where we take a first principles approach to understanding how blockchains work. Today, we're going to be talking about one of the most important fundamentals of blockchains, cryptographic hash functions. Cryptographic hash functions are used for many things, including digital signatures, MACs or message authentication codes to verify the integrity of data, key derivation, random number generation, and more. They're used extensively in blockchains for things like not having to store the entire history of everyone's transactions, being able to easily check that everyone has the same history, and for proof-of-work mining, which is an integral part of Bitcoin. Examples of hash functions that you will encounter in Bitcoin, Ethereum, and other blockchains include RIPE-MD160, SHA-256, Ketchak-256, and SHA-3. Hash functions are deterministic functions that can take in any input data, but will always return a fixed size output. This input, which is often called a message, can be anything from a few characters to an entire movie file. But the important part is that no matter the size of the input, the output hash will always be the same size. A lot of times, the output size is specified in the name of the hash function. In the case of functions like Ketchak-256 and SHA-256, the output is always going to be 256 bits. The function being deterministic means that the same input will always have the same exact output. So let's take a look at one of these cryptographic hash functions in action.
So here we have the Ketchak-256 hash function. We can put in any data as an input and the function will output the 256-bit hash. Now, as I mentioned, the input could be any length. So we can add a bunch of characters, let's just copy and paste this a bunch of times, and the hash will always be the same 256-bit length. We could even have data that's super small, like an empty input. We can hash information that needs to be signed. For example, we could hash information about a transaction. So this could be a very, very basic transaction of me sending $10,000 to you. And then we can hash this, I could digitally sign it. And although the transaction data in real cryptocurrencies and blockchains is a little bit more complicated than this, this is what is done.
Now I know at first glance, these output hashes of a bunch of letters and numbers look really complicated. But they're really just huge numbers that are being represented in hexadecimal, or base 16. Now here's this output number, represented in a way that we're more used to seeing numbers. Or we can look at the hash as a string of 256 bits, which are just ones and zeros. The next property of cryptographic hash functions is that we want them to be easy to calculate. One of the big use cases of hash functions is to verify the integrity of data. For example, let's say we both have a movie file, and we want to check that we have the same exact version of this movie. An easy way to do this is to hash our movie files and check to make sure we have the same hash. We want everyone to be able to use these functions to easily verify data. So we need them to work relatively fast, even if the input is large. Another use case of cryptographic hash functions is for pseudo-random number generation. So if we even just slightly change an input, we want the function to have what's called an avalanche effect, and have the output of this slightly changed hash to appear completely different and random. This means we want the output to seem as if we just flipped a new coin for every bit in the output. This property is particularly relevant in the process of proof-of-work mining. If you're not familiar with proof-of-work, I'll be covering it in another video, but it's the basis of how blockchains like Bitcoin are secured. This randomness property means that you can't manipulate the input in ways to get specific kinds of outputs. Let's say some Bitcoin miner figured out a trick where they could choose certain inputs to a cryptographic hash function and know how the output would change. That would actually give this miner an unfair advantage in the Bitcoin network. The next property of cryptographic hash functions is one-wayness. This property states that it should not be possible to calculate the input data given the output hash, unless you just try every possible input. Now it might seem obvious that you can't take this string of 256 bits and turn it back into a full 2 GB movie file. But this property of one-wayness means that you shouldn't be able to figure out anything about the input given just the output. You shouldn't even be able to do something like look at a hash and figure out if the input was an odd or an even number. For the next two properties, it's really important that we define what is called a collision. A collision occurs when two different inputs to a hash function have the same exact output hash. In non-cryptographic hash functions, collisions happen a lot, and it makes sense that collisions have to exist for every hash function. If we say that the input can be any data of any size, but the output has to be this fixed string of 256 bits, there are going to be a lot more different inputs than different outputs, and this means that there has to be collisions. But not encountering any collisions is actually an essential property of cryptographic hash functions. When we find a collision for a cryptographic hash function, we consider the function broken, and we stop using it completely, and need to create a new and better function as a result. One property that you'll hear about a lot is weak collision resistance, which is also referred to as second pre-image resistance. This property states that, given a specific input, x, it should be extremely difficult to find any second input which has the same exact output hash as x. One of the major use cases of hash functions is to hash data and then digitally sign that hashed data. So I might create a transaction that says to send $10 to Carl. And I will hash this transaction data and then digitally sign it to verify that I really did want to send $10 to Carl. Now, if Carl could manipulate some data of a new transaction that says Kevin sends $10 million to Carl so that it has the same exact hash, Carl could get paid $10 million because it would appear as if I signed the hash of this $10 million transaction. This is clearly really bad, and we want to avoid this at all costs. However, we want to go one step further with cryptographic hash functions and have the property of collision resistance, which says that we can't have any collisions at all. But why do we care if some movie file happens to have the same hash as some email message? Well, to be honest, we don't. But there are so many different possible output hashes that when people find collisions, it's not that they've just happened to stumble upon one. Usually, there's some sort of method or trick that researchers have found to be able to manufacture a collision. Because cryptographic hash functions are widely used to verify the integrity of data, they're completely useless if two people could have two different pieces of data that have the same hash. In blockchains, hash functions are used to allow people to easily verify that everyone has the same version of transaction history by just checking a single hash. If collisions could be created, there could be a case where half of the participants in a blockchain network have one version of the blockchain, and the other half have a completely different version of history. But they're all fooled into thinking that they have the same version because they compare hashes and the hashes check out. So now to recap, cryptographic hash functions are used in blockchains to allow messages to be digitally signed. They're also used to verify data integrity of the blockchain to make sure everyone has the same history of transactions and state. And cryptographic hash functions are used to generate pseudo-random numbers in proof-of-work mining, which is used to secure protocols like Bitcoin. Now, the main properties that we need from cryptographic hash functions in order for them to work for these use cases are that they can have input data of any size, but will always output a hash of a fixed size. They are deterministic, so the same input will always have the same output. They are fast, they appear random and exhibit an avalanche effect, they only work in one direction, and they are collision resistant. Many of these properties are connected and interrelated. For example, if you have a situation where output bears no relation to an input and it looks random, and the output is 256 bits, you'll probably get a large part of collision resistance. This also means that if you just break one of these properties, other properties could be affected. So for example, if an output doesn't actually appear random, it'll be a lot easier to find collisions and then break the function. Typically, these properties are things that you hope for, but you can't guarantee. The only security that we have that the current generation of cryptographic hash functions won't be broken is that researchers are trying to break them and haven't yet. If there's ever a theoretical attack that could find collisions with a feasible amount of computing power, then a new hash function must be created. This is what happened with SHA-1, where attacks have been theorized since 2005, and researchers competed to create the next generation of hash functions. Thanks for watching this episode of Blockchain Fundamentals, and I'll catch you next time when I cover public-private key cryptography.